Yeah, all right. Good morning, everyone. So it's my great pleasure to introduce Rahul Razdan. He's the CEO of Razdan Research Institute. How cool is that? You have your own institute. And so Rahul has actually is a very seasoned scientist and has a lot of experience working in the world of verification IP, and has his hands, equally in academia, in startups, and has a whole lifetime of experience with Fortune 500 companies. And so today he's going to talk to us about this very exciting project called PolyVerif, an open source framework for autonomous vehicle verification and validation. And Rahul Razdan is also a director of the Autoware COE Center in Florida Polytechnic University. This is a network of many universities that work together on building open source autonomous vehicle software with Autoware. So welcome, Rahul. We're very excited to hear your talk.
Well, thank you, Rahul. Yeah, so let me just for the whoever may be listening, if you want to get a hold of me, there's an email address, and if you want to look at the actual open source environment, which will probably be more interesting, you can get it at www.avvc.net. Okay. I just thought I'd do a slight introduction of the university. Most of my university work was in Massachusetts, and I also went to CMU. And then what I knew of Florida was there was University of Florida, University of Central Florida, and University of South Florida, and North Florida. It's all of this. It seems very confusing. So I want to add one more, which is Florida Polytechnic University. So this is the latest university in the state of Florida system. So just to give you some sense of it, the state of Florida system is the second largest, I think maybe the third largest system, Berkeley, Texas, Florida system. It's a massive public system. Florida Poly is the latest. It's only about 6 years old, and it's a polytechnic, and it has degrees in various programs. It's not very big, about 1,500 students, but growing. And relative to our topic today, autonomous vehicles, next to the university is a large testing facility called SunTrax, funded by FDOT. For AV testing. They've put, I don't know, a couple of $100 million into it. The state of Florida has also invested in a research center at Florida Poly called AMI, Advanced Mobility Institute. And that center has subsequently gotten NSF funding and industry funding and so on. So the center does a lot of research, mostly focused on autonomous vehicle verification and validation. Obviously, education, courses, things like that, and industry thought leadership, and all that has to do with working with people like SAE. Rahul gave a brief background. I just want to give an orientation of how I'm coming at this problem. So I was a CPU designer for a long time. Ran a big chunk of Cadence Design Systems, especially their verification business, and I've done a fair amount of startups. So when I look at the AV validation and verification problem, a lot of the techniques that we'll talk about are coming from the deep experience we have in validation and verification in the semiconductor and electronics space. If you're interested in any of my work, I have kind of 4 places. There's the open source environment. There's a lot of work with SAE, books, reports, things like that. And if you want to read something light, you can go to Forbes, where there's a bit of humor and some opinion as well. Okay. One report I would encourage you in this space to look at is this Untitled Technology and the Autonomous Vehicle Test and Validation. It's a fairly complete look at the open issues that we have in V&V. This was written, I don't know, 3 years ago, by myself and with a group of other people. These are the group of other people, and I think it's borne out that the issues we thought would happen are actually happening. Okay, now we get to the meat of the matter. So I'll start off with a basic level, AI. so what is AI and what do we mean by AI? And of course, coming from Carnegie Mellon, there have been various generations of AI, but the latest in manifestation of AI is this machine learning paradigm. And the way I think of this machine learning paradigm is it's sort of the next iteration of abstraction. So, if you wanted to build function and if you want to build with hardware, which you can, that has advantages and it has disadvantages. Principally, you have to build the hardware and you have to iterate on the actual manufacturing. The next big jump in abstraction was the processor abstraction, which generated this idea of software. And of course, the great value of that was with this abstraction level, hardware and software could work separately and iterate separately and through this intermediate form. And the only problem is you have to have boatloads of software engineers to actually build function. And the value of machine learning based AI is, okay, you can actually have data molded appropriately by a small number of individuals, build function through training and then implement it through inference. And I on the right is the automotive equivalent of this. Many other industries have similar forms. Okay, so AI is actually a very fundamental thing, much like software, and this is the reason it's proliferating across all markets. Now, much like the jump from hardware to software, we as an industry and academia had to struggle with the differences between those two paradigms. And the jump up to AI, you kind of reach the next level. It's you can form function, but there are differences between software and AI. And as an example, this is a list which, with the fullness of time, I won't go totally through, but most of the people that are on this call or will listen to this will be very aware of these issues, that ML-based algorithms or AI-based algorithms, they don't really have a logical theory. They're not analyzable. There's correlation versus causality. They're not deterministic in nature. And really, they're unknown computational complexity. And these create fundamental issues, especially for validation and verification. There's an article, by the way, I wrote on Forbes, which is meant to be sort of, entertaining to some sense, which makes the mapping between physics and kind of, relativistic Einstein physics and quantum physics, and I'll say traditional software and AI. And the mappings are quite interesting, actually, because one is probabilistic and both are the power of probabilistic methods is apparent in both. Okay, so what are the challenges? Well, AI is very powerful, except we don't really know much about it in the sense that what is the right AI model and why is not entirely clear. Certainly, there's no real theory around it. It's mostly empirical. Most of the arguments that you hear are, we tried this, it seems to work. That's kind of the basic argument. Will the model converge? There's really no theory on that. And so, if you would try to model through AI methods, something as simple as addition, you want to do vision, natural language processing, and this is the final one, is meant to be, I guess the term would be triggering, astrology. They all fundamentally look the same, and so there is no real theory of convergence. And then, of course, AI models are quite susceptible to noise, and robustness to noise is obviously a big issue. So the question is, how do you become robust to noise, and then how do you define noise fundamentally in the context of the training paradigm that exists? There's a lot more details below this. I mean, I've written a lot of articles around the core of these challenges, but these are the high level challenges. And so fundamentally, how do you know it works, right? You build something, how do you know it works? So what are the current approaches? Well, you sort of have a system level design based approach. That is, you define a higher level function that is fairly well understood, and the AI components are within that function. And the only difference between software and AI is AI just happens to be software that's generated through this machine learning paradigm. And so that this structure is actually not bad if you have a system level model or some higher level form that you can test against, but it's still problematic. So the AI models themselves have no fundamental structure as opposed to software. And so this creates this exacerbates this problem of where do you test and how do you validate that you're testing the interesting edge conditions, and how do you even find the edge? Obviously, the model itself was built from training data. So how do you manage groups of training data? How do you separate noise in the data versus the real data? And then how do you look at the training data versus the ODD you're going against? These are all fairly fundamental problems that are out there. And how do you measure completeness? That's always a big issue. Um, um, this is in the paradigm where you have a system model. Now, the interesting thing is many people like to use AI in places where the fundamental system model or specification is actually hard to write. I mean, vision is a good example of this. And in that case, you from a validation and verification point of view, you have an additional problem. How do you determine correctness? Because you don't have a spec to go against, right? So the question becomes, so these are kind of the approaches, and there are other people that have tried other methods. Assertion-based methods are things that are out there. So you can't do a specification of what works, but what you specify is what the error conditions are, and you try to make sure through assertions you try to make sure that these that you never violate those assertions. In the case of transportation, that might be you never have collisions, or you never have some bad things happen, right? Yeah, there's a lot of content here, which I don't know if I want to get through. The bottom line of all of this is it's a huge problem. We don't really know how to do validation and verification of AI. And so there's a need for a research platform to accelerate this learning curve. This is the motivation for all of this. So in the case of AV, we at Poly and then with some other partners have said, okay, well, let's go build this research platform. And our objective is to build a open source platform. Why? Because we suspect, well, there are three reasons to do open source. One is to actually get at the right pieces of data, you might have to go to the innards of the actual algorithms. So access, open source provide access that's interesting. Number two, if you build a fairly robust open source environment, then you could contribute to it and take from it. And so you don't have to build the rest of it. So as an example, I'll show in this case, we have a fairly robust environment. And if somebody wanted to work on a very specific thing, such as, how do I do better location services? Or how do I even test in a better way location services? They can work on just that part, and everything else is available to them for the testing infrastructure. And so that's the second reason. And obviously the third reason is it's in the context of open source and a well-functioning environment, people can contribute back, which accelerates the whole state of the art. So for those reasons, we've done an open source environment. And so the players, Florida Poly is a player, Embry-Riddle, Caltech in Estonia, and UC Berkeley. So UC Berkeley is mostly from the scenic stuff. Teltech, they've built an Autoware based shuttle. And so they have a physical shuttle. So as an example, if somebody wanted to do something in Autoware and then actually test it in a physical environment, which we've done as an example, there's an ability to do that. Embry-Riddle's done a lot of work in the modeling old test cases, such as all the accidents that in the California database, modeling that so that they're available in this open source environment. And we've architected this environment, and then we're sort of funding the early development of it. With this, you have course materials, a lot of other information which you can just find on the website. So now, Autoware we chose Autoware because it was open source principally as the center point for this open source environment, and the reason is pretty simple. It's an example AV stack. We don't really particularly care about the details of it. I know that's a strong thing to say because our focus is the validation and verification, but it provides a good basic starting point. And if somebody wants to put in their own stack, it provides a mechanism to build interfaces such that somebody can do that, right? So we have Autoware as a starting point. Within the stack, we have the following capabilities. We have an ability to build a digital twin through a variety of flows. You can go into you can basically take a topology. It could be a pen, and what we can do is through Google Maps and Google Earth, we can build a digital twin in this environment. Or if you wanted to have a drone fly through that topology, that will improve the digital twin fidelity. Once the digital twin is built, you can introduce active actors such as cars, trucks, pedestrians, the typical sort of thing that you would like. The physics is modeled at the level of the simulator, so there's various simulators that are supported. You can see them: Sumo and LGSCL, Carla. Tier 4 has a simulator we're looking at integrating, and so on. And the notion is that's the basic layerings that allows you to build a model, to simulate the model with some level of physics, and then there's a test generation, symbolic test generation with scenic that's available. That's the baseline, and on top of that, we call polyflows, some specific flows that are built to demonstrate the design for experiment structure for particular parts of the Autoware universe, right? So as an example, these are the various flows that are also in this open source environment. So we have a detection validation flow, whose objective, of course, is to figure out, do the sensors actually see the objects of interest? And of course, the thing you're trying to figure out is, in this topology, with the introduction of noise, which tries to model things like weather or other obstructions, does the unit under test see these objects just at a level of detection? And if so, if not, what are the issues? And if so, when? And then you build metrics around all of this stuff to figure out correctness. Perception is the next stage. And so, okay, having detected these objects, can you recognize them in order to be able to determine their future movement? Similarly, location validation. So do you know where you are? And there's, as you know, there are both global and local methods for location. detection, and you want to be able to introduce noise in both in order to figure out from a validation and verification point of view that the algorithms are robust. Control validation, these are for things like ADAS, kind of cruise control following kinds of methods. And then decision validation, which is, you had a higher level objective of going from A to B. Did you actually get there? And did you violate anything along the way? So these are the sort of things built on top of the basic environment, and what you can imagine is a software infrastructure which has instrumented everything and the simulators in such a way that you're able to in Scenic build a test environment or a design for test. And then as an output, you get a number of reports. And then on top of those reports through software, you can build whatever pass-fail metrics that you like. And so these are the various kinds of reports that are built and available in this environment. In your mind, the way you should think about this is the objective of this is not to say this is the way you do validation. The objective of this is to say, here's an example. And as an example, if Rahul, you had a graduate student that said, I have an idea for how to do, location validation in a better way, and I want to model some particular effect in a better way. The notion is they can go into this part, manipulate only the pieces that they need to manipulate, and have available the rest of the environment in order to very quickly advance the state of the art. That's the objective of this, although these on their own have some amount of value.
So Rahul, I just had a quick question on that slide.
Yeah, of course.
So this is allowing the capture of, say, certain scenarios, and then because when we use these words, verification and validation, different communities have a different meaning for them. The words are very overloaded. So is this like a scenario-based test system, or is it more of like a framework? Use whatever backend verification tool you like, but this will allow you to capture the scenarios, extract the data, and then or is it like a testing falsification framework?
No, the way to think of it fundamentally as a simulation framework, okay, with one of various simulators. The simulators have typically, at the very least, are modeling the visual and the Newtonian mass aspects fairly well. But if you go to other sensor types like LiDAR or radar, that depending on the simulators, you'll have a different level of fidelity. So in your mind, imagine a simulation of a real environment. Like I'll show you examples. We've gone into Jacksonville or Talon, and we've taken where somebody wanted to run their autonomous vehicle routes. And we take that environment and we model it inside this, through a digital twinning process inside the simulator. So think of that as the static piece that you build. And then you have dynamic pieces, pedestrians, trucks, whatever else you want, which you can introduce. And through Scenic, if you're familiar with Scenic, so typically the problem you run into with test generation is, you build a very particular test, and that has its own value. But what you really want to do is symbolically specify tests so that you can have automation through a random number generator that can look at all sorts of variations. So Scenic is, and by the way, before Scenic, I did this in hardware design, 30 years ago. We did this all the time, right? So think of what we built as simulator, a digital twinning process, attaching Scenic so you can build any kind of scenario that you want on top of this infrastructure, okay? And then think of kind of a software infrastructure where you can come in and say, I want to model, so simulating something in a simulator on its own is while interesting, not so interesting from a validation verification point of view.
Yeah.
What you really want to do is say, okay, how do I model realistic noise? And the noise can be of various flavors. As an example, in the detection phase in Jacksonville, we modeled rain because it rains a lot in Jacksonville. So then, in the context of this rain, we asked the question: okay, what is the degradation of the sensors caused by this rain, and what's the result of that degradation relative to the other parts of the stack, right? Okay, so you can easily do things like that in this environment. And let's say you come along, and this is my point. Somebody says, well, your model for rain is not very accurate. We would say, okay, build your own, just stick it in.
Yeah. Makes sense.
So so it's both a framework, but also it has a fundamental model of validation or verification that we're trying to support. We are missing one piece. So one piece we're going to add at some point soon is coverage buckets, right? So we don't have a notion of coverage in the environment yet. If somebody wanted to put it in, that would be great, but eventually we'll put it in. Right. And our driving factors are, we're working with various cities, especially in the state of Florida, that are rolling out AV tests, AV shuttles. And so we're working with them using this environment as a vehicle for them to set their safety standards, right? So as an example, there's a large project going on in Jacksonville with JTA where they're rolling out AV shuttles, and they have a very fundamental question: how do we know whether whatever the vendors are selling us works? Does it work in our environment? How do we know it works under rain or other conditions that we care about? So these are the sort of things that we can enable in this environment. Did I answer your question?
Yeah. No, I think this is great, and I think even from testing or any standpoint, this provides a very good starting place where you've connected all like a lot of the important elements that before.
That's exactly, I just know the difficulty. If, as somebody comes in and says, I have a great idea either for validation or core, maybe they have an idea for a core perception function. I mean, let me give you a real example. The MIT guys are looking at movement-based training. So now the question is, how do you know it works? And so this is like we're trying to advance the state of the art by enabling people to quickly experiment and hopefully add value along the way, in the sense of just contributing to this environment. It's on GitHub. Anybody can look at it. There's no cost to it. It's a straight model, right? We're not. It's very much meant to be an effort that moves things forward, as it were. Now, on top of this actual software infrastructure and digital twinning process, let me see. I'll just. This is describing the Berkeley, the scenic environment and all of that sort of stuff. And this is so on top of this, we also are providing existing environments. So as I said, Embry-Riddle has taken this database of AV accidents from California, and we've modeled that in this environment. So just as an example, if somebody had a bright idea for accident, triage or diagnostics or whatever, on top of the software environment, our objective is to provide real data, real digital twins that they can test against, so they don't have to do that problem. So we have that one that's available. We will have so we have JTA's environment. Yeah, so Taltech, so their routes and all that information is now available. So by the way, the advantage of this is snow. You don't have to have snow to get snowy environments, things like that. And then the last one is JTA. So in your mind, the way you should think about this is there's a software environment, and which has basic capabilities, and think of it more as a software infrastructure. Then you have the ability to go in anyways, because it's open source. You can change anything you want and build a derivative of your own. And then finally, there is existing AV situation. So JTA, Taltech, and then these AV accidents from California. That data that's available. So that'll all be in the open source environment. Actually, is already in the open source environment. Maybe one more thing. Actually, I don't know.
So I think Rahul, before you continue, Ruben had a question. Maybe
go ahead.
Ruben,
Go ahead.
it's because Rahul may not see the chats, so you can just ask him a question.
I was also speaking, but I think you couldn't hear me about the validation pillars. So it looks like they're completely independent on that slide. However, I would think it also makes sense to run, for example, the mission planning validation with an actual perception twin. Is that something that you're doing?
Well, no, you run all of so all of them are running concurrently, right? And so several things. I mean, I'm struggling with describing two different vectors at the same time. I'm trying to describe the environment to an audience of researchers that say, okay, how do I use this environment for what I do? But then there's a very separate question of what should be the way you do validation. And so the the environment about, think of that as a software and data that's available to you. That's kind of the way. In terms of how you should do it, certainly I have very strong opinions on this, and my part of this is part of the reason we're using Autoware also is we think that AD validation will build up from component level validation through abstraction levels that interconnect with each other. And there's very much, like from our experience in semiconductors, we take quantum physics level effects that are happening at a device level, and then we interconnect that through abstraction all the way up to processors, right? So the automotive industry and certainly the AV industry has not gone through that level of work, which I think they will need to do. And so we, on our own research, we are starting to define these intermediate abstraction levels, and then trying to figure out how can you interconnect them in such a way that you can have guarantees on both sides, which is really how it works in for example, chip design. So I don't know if that answered your question, but you will see articles like technical articles from us on that vector, I think, very soon. Where we talk about component level verification and abstraction levels between the components that need to be exposed, and they'll need to be standardized also, right? That's the other aspect of this. And by the way, this is one of the big advantages that I see for something like Autoware, which is, as a experimental open source stack, it's okay. It's much more interesting from my point of view as a vehicle to understand what should be these intermediate interfaces and how to use them. I do want to make one final point, which is so I've been I on the industry side or on the academic side, the notion of open source interfaces that or open source software that's made available sounds attractive, but of course, when you really try to use it, what happens is who's maintaining it? And in the academic environment, that maintenance structure is very difficult to do because graduate students leave. So one of the other differences that we did in this environment versus the traditional path is I hired a services company, this company, Clevis, and they maintain this environment. So as an example, if you're in industry or you're in academia, and you want to somehow use this environment or have somebody else do the implementation, there's an ability for a services firm to do all that for you as well as maintain it. And so so that's a very important point, because otherwise what happens is it becomes very fractious. Things don't hold together unless somebody's standing behind it. Okay. Yeah, I don't know. Did I answer your question, Ruben?
I think you did. Yeah.
Yeah.
Thanks.
All right. Well, I'm basically done. I can talk about many other things, but let's see. You tell me, what are you guys interested? I mean, we can get into the details of any of this sort of stuff. It's a small group.
Yeah,
So I'm currently dealing with a question how you get from the high level requirements down to data set requirements. And I think you said in the beginning that there would be a gap, right?
Yes.
So there were the open questions in the beginning, and you also didn't promise to answer them, I think, on the first two slides.
Yeah. So
right.
Go ahead. Yeah.
So if you have any ideas there, what would be?
Well, I do. Yeah. I mean,
yeah.
So it's very important. I mean, it's good you're talking about specs, because specs as well as expectation functions are, and I don't know what particular area you're talking about, but as an example, one of the real issues we have, again, in the automotive industry and even with ADAS, is that there's no real clear understanding of the expectations, and therefore specs, around many of the functions that are even on the road today, right? So if there are specs, that's the first good starting point. The specs typically derive from the specs. You can derive the ODD as well as the testing infrastructure required. And so I think that's kind of that is the way that it will go. I mean, the current state of ADAS is and I'm talking, you're not even talking about AV, I'm talking about ADAS. The current state of the ADAS is extremely poor. I mean, most customers that buy this functionality don't actually know what they're buying. And so the expectation setting process is actually quite problematic. By the way, one other part of this is there's an issue of third-party effects. We again, in the industry, we haven't had this conversation, which comes down to, if somebody is in autonomous mode, do you as a third party have the right to know when they're in autonomous mode? And currently we don't tell them, because we expect, it behaves as if there's a human there. But from a legal liability point of view, there's going to be I think a process where that's another form of communication that needs to be built into the system. What else?
Great. So Rahul, I'll just stop the recording and we can have the discussion now.
Yeah.